Hello students, welcome to today's classes. Now we are going to see the quick revision in isomerism. What are isomers? Isomers. Iso means same, mers means parts in Greek language. Definition: the same formula but differ in physical and chemical properties. Same formula. The molecular formula is same, but the properties are different. That is isomers. Now see the example C4H10O. The molecular formula is same for alcohol and ether, but structural formula is different. The properties are also different. The same molecular formula, different physical and chemical properties are known as isomers. The phenomena is isomerism. Now, the isomerism is classified mainly into structural isomerism and stereoisomerism. Structural isomerism again classified into chain isomerism, position isomerism, functional isomerism, metamerism, tautomerism, ring chain isomerism. Stereoisomerism is classified into geometrical isomerism and optical isomerism. Now, what is structural isomerism? Already we have seen what is isomers. Here, the isomer is going to differ in structure. Which differ in structure, they are known as structural isomerism. The first one is chain isomerism. Chain isomerism is also known as nuclear isomerism or skeletal isomerism. Difference in carbon chain. So for this, minimum of 4 carbons are required. When we look at the structure A, there is 4 carbons are there. In B, in a long chain, there is only 3 carbons. There is a difference in number of carbon atoms. So, it comes under chain isomerism. In C4H10, only 2 isomers are possible. Similarly, C5H12, 3 isomers. C6H14, 5 isomers. C7H16, 9 isomers are possible. Now, position isomerism. Difference in position of a substitute or a functional group or multiple bond. Now, what are the multiple bonds? Double bond or triple bond. When we look at the example A, the double bond is at first carbon atom. When we look at B, the double bond is at second carbon atom. There is a difference in its position. One more example for position isomerism. Benzene ring, which is attached to 2 chlorine atoms. How many possible structures are there? That is only 3. 1 and 2 ortho, 1 and 3 meta, 1 and 4 para. Only 3 possible structures are there. So, for this, position isomers are 3. Functional isomerism. There is a difference in type of functional group. Now, alcohol OH becomes ether O. When we look at the examples, alcohol and ether. Similarly, aldehyde becomes ketone. Carboxylic acid becomes esters. Some more examples. Cyanide becomes isocyanide. Nitro becomes nitrite. Amines. In this amines, what are the amines? The derivatives of ammonia. Now look at that one. That is ammonia is there. The hydrogen is replaced by one alkyl group. That is primary. If 2 hydrogens are replaced by 2 alkyl groups, that is secondary. 3 hydrogens are replaced by 3 alkyl groups, that is tertiary. Now, these primary, secondary and tertiary are degrees. Primary, secondary, tertiary. So, based on the degrees, it also comes under functional isomerism. Metamerism. Different alkyl groups are attached to a bivalent. What is bivalent? Valence is 2. Oxygen is with valency 2. It connects with 2 different alkyl groups. Now, we are going to see what is alkyl. If you are going to remove one hydrogen from alkane, that is alkyl. See the example. By removal of one hydrogen from CH4, that is CH3. Always no need to count the number of hydrogens. If there is only one carbon is there, that is methyl. 2 carbons are there, ethyl. 3 carbons are there, propyl. Tautomerism. It is a special type of a functional isomerism. Hydrogen oscillates between 2 molecules. They are dynamic in equilibrium. Here we have to see the conditions. There should be a multiple bond. C double bond O, N double bond O, S double bond O and C double bond N. One more condition is there should be at least one alpha hydrogen with sp3 hybridization. What is alpha hydrogen? In A, the carbon which is connected to a substitute. Chlorine is a substitute, is connected to a carbon. That carbon is alpha carbon. In B, C double bond O, ketone, is a functional group. Next to functional group is a alpha carbon, either left side or right side. Then what is alpha hydrogen? The hydrogens, those are connected to alpha carbon, are known as alpha hydrogens. Now, what is hybridization? The intermixing of atomic orbitals of same atom are known as hybridization. How it is calculated? Many ways are there, but out of that, one method is based on sigma bonds. Around carbon atom, how many sigma bonds are there? There is 4 sigma bonds are there. If 4 sigma bonds are there, that is sp3 hybridization. Now, so that is hybridization is sp3. Now, we are going to see some examples. In tautomerism, A, B, C examples has been given. Now in A, function group C double bond O ketone is there. Beside of that, that is an alpha carbon. 2 alpha carbons are there. 4 alpha hydrogens are there. But as per condition, 1 alpha hydrogen with sp3 hybridization is sufficient. But here more than required. That's why no doubt at all it shows tautomerism. When we come to the B, there is alpha hydrogen, but that is not sp3 hybridization. When we come to C, there is no alpha hydrogen. That's why A shows tautomerism, B and C does not show tautomerism. Now, there is one exception. Many more exceptions are there. Out of that, one exception. The bridgehead atom. Which is bridgehead atom? The 2 carbons Those are common for two rings. They are known as bridgehead atoms. These bridgehead atoms does not participate in tautomerism. Why? Because the hydrogen, when it is removed, the pi bond is going to be formed. The pi bond does not exist at bridgehead position. Ring chain isomerism. There is a difference in ring and chain. Same formula, but structure is different. One is in a ring, one is in a chain. That's why it is a ring chain isomerism. Stereoisomerism. Same molecular formula, but differ in spatial arrangement. Here, two are there. They are geometrical isomerism and optical isomerism. Geometrical isomerism. Difference in spatial arrangement of atoms around the double bond. Now, when we look at the structure, C double bond C is there. With respect to C double bond C, how they are arranged? They are at the same side or in opposite side. Geometrical isomers, if there is a condition is there. What is that condition? The double bonded carbon should contain different atoms or groups. When we look at the example A, C double bond C, the C connected to two hydrogen atoms. Hydrogen atoms are same, similar. That's why A does not exhibit geometrical isomerism. When we come to B, the C is connected to methyl and hydrogen. Definitely, it shows geometrical isomerism. Cis and trans. In Latin, cis means one side, trans means opposite side. Cis isomer, what does that mean? The similar atoms or groups are attached to double bonded carbon at the same side. Trans isomers. The similar atoms or groups attached to double bonded carbon in opposite side. We'll see the example, then you will be able to understand very clearly. The properties of cis. What is cis isomer? Same atom or group of atoms attached to same side of the double bonded two carbon atoms. Here mu is not equal to 0. What is mu? Dipole moment. Why it is not equal to 0? The two group of atoms are pulling towards itself. That's why there is a moment in a molecule that is known as dipole moment. Actually, the dipole moment is the product of charge and distance. But here you have to remember that that is a moment due to charge. Is a dipole moment. Dipole moment is not equal to 0 for cis. Then dipole moment, pole means charge. Because of that charge, because of polarity, they are more soluble. Because of the charge, the force of attractions are very strong. That's why boiling point is more for cis. Now here what we should remember? The properties of cis isomerism. One is dipole moment is not equal to 0. They are more soluble. Their boiling point also more. Now, in geometrical isomerism, trans isomerism. In trans, the dipole moment is equal to 0. Why? They are in opposite sides. the dipole moment is equal to 0. How could you say that? They are pulling in opposite directions. They are more stable. Stability is more. The trans is more stable than cis. These are closely packed. That's why melting point are more. It required more energy to break the bonds. In optical isomerism, the same physical and chemical properties, but differ to rotate the plane of polarized light. The light is going to rotate left or right. If glucose and fructose are there, same molecular formula, but it is going to differ to rotate plane of polarized light. If glucose is there, light rotates right side. If fructose is there, light rotates left side. Based on that, we can say that which is glucose and fructose by using polarimeter. In optical isomerism, condition number 1, there should be a chiral carbon. Which is a chiral carbon? A carbon which is connected to 4 different groups. Atoms are group of atoms. That is a chiral carbon or asymmetrical carbon. It is optically active. What does it mean? It can rotate clockwise direction or anti-clockwise direction. Optically active. Condition number 2. If two chiral carbons are there, then we have to see plane of symmetry is there. If plane of symmetry is there, that is optically inactive. How to identify the plane of symmetry? That's your doubt. I'll clarify your doubt. Now look at the alphabet A, B, C, D, E. Now I'm going to take only one example A. If I will draw a vertical line, the A is going to break into two identical halves. Similarly, B, C, D, E. But F, there is no plane of symmetry. If there is no plane of symmetry, then it is optically active. Now again, see the previous example. That is, there is a two chiral carbons are there. But if you draw a line between hydrogen and hydroxyl group, it gives two identical halves. That's why it is optically inactive. Nomenclature in optical isomerism. There is two methods are there. One is relative configuration, second one is absolute configuration. In relative configuration, with reference to glyceraldehyde. So see the structure, how it is. The OH with respect to CH2OH, with respect to CH2OH, the OH is at right side, that is D notation. OH, if it is left side with respect to CH2OH, that is L notation. That is DL notation with respect to glyceraldehyde. Now, look at example glucose. That is the glucose structure. When we look at the structure, with respect to CH2OH, OH is at the right side. So, that is glucose comes under D notation. Absolute configuration. Very good. The vertical line with least priority based on their atomic number. Atomic number is lowest for hydrogen. That is placed in a vertical line. That is very good. If it is in vertical line, then R configuration becomes R, S becomes S. Then what happens, sir? If it is in a horizontal, then R becomes S, S becomes R. How to identify? Based on Zipf's rule. What is Zipf's rule? That is, in Zipf's rule, we have to remember ZAM, JA. Z stands for atomic number. We have to remember atomic numbers. A stands for mass number. M stands for multiple bonds. The first priority goes to atomic number. If atomic number is same, then only we have to go for mass number. Then what is multiple bonds? For example, carbon is there. Carbon is connected to one oxygen atom. So here, how many oxygen atoms are there? 1 and 2. Like that you have to consider. See the example, lactic acid. Now here, in a vertical line, there is the least priority atom is there. Look at this example, lactic acid. In a vertical line, there is a hydrogen atom, that is whose atomic number is very low. The least priority for hydrogen atom. Now, it is connected to oxygen, carbon and carbon. So, oxygen, carbon and carbon, whose atomic number is more? Oxygen atomic number is more. That's why we have to give the priority to oxygen atom. Next one, two carbon atoms are there. To whom we have to give the priority? Then we have to say next atom. That is oxygen. Here hydrogen. So priority, second priority to COOH. Already I said that the two bonds are there. We have to consider two oxygen atoms. The third priority CH3. Fourth priority hydrogen. When we move from OH, first priority, second priority aldehyde C double bond OH, third priority CH3. It is a rotating in anticlockwise direction. That's why that is a S configuration. Optical isomerism. What are enantiomers? Non-superimposable mirror images. See, M stands for mirror. That is lactic acid is there. It is a mirror image for that one. These two are not going to superimpose. Now look at this one. For this is the mirror image. These two are not going to superimpose. Non-superimposable mirror images are known as enantiomers. Diastereomers. For a given compound A and B, these two are not the mirror images. They are not mirror images. They are not superimposable. That is known as diastereomers. Mesomer. It is optically inactive due to plane of symmetry. A line is passes through hydrogen and hydroxyl group. The two identical arcs due to internal compensation within a molecule. One is clockwise, second one is anti-clockwise. That's why it is optically inactive. Racemic mixture. That is equimolar mixtures of pairs of enantiomers. For example, one molecule is dextrorotatory, one molecule is levorotatory. When you are going to mix these two, so optically inactive due to external compensation. In mesomer, within a molecule. In racemic mixture, that is between the molecules. That's why it is a external compensation, optically inactive. Resolution. The separation of enantiomers from a racemic mixture is known as resolution. Isomerism. Racemic mixture can be separated by mechanical separation, chemical separation, or biological separation. It cannot be separated by fractional crystallization, and chromatography. absolutely free. Chemistry assignments are available at www.delayedclasses.com. Hello students, I hope that it is more useful for you. You must subscribe. Why? Because you should not miss the next classes. See you. Bye.